Hi everyone, I'm Yaniv, co-founder and CTO of Endor. Black magic. Not black magic, just math. So Endor is an MIT spin-off company, financially backed by Google's Eric Schmidt. The company exclusively leverages the new science of social physics that was developed at MIT by myself and our other co-founder, Professor Sandy Pentland. Social physics is a novel mathematical modeling of crowd behavior that allows the automatic prediction of customers' behavior. I received this photo yesterday. It was taken last week at a lecture given by Jeff Dean from Google. Can we replace machine learning expertise with a lot of computation? Personally, I find this question to be one of the most interesting and exciting challenges in science today. But before I give my view on it, I would like to discuss a little bit of how things are being done today. So when we talk about predictive analytics, the distance from an idea to an actionable business insight is very, very long and expensive. Whenever a new project that requires predictive capabilities comes along, companies' internal data teams undergo a long, iterative, manual, frustrating, horrible process that takes weeks, if not months, to converge to a working model. And this is being done from scratch for every question, creating a very frustrating bottleneck. And the question is, why is it the case? Why does every company find itself with this process? Some people say it's a talent issue. Let's bring better data scientists or more data scientists, and this bottleneck will disappear. But this is not the case. What we have here is actually a technological gap. The prevailing science of today, all the technologies that we have today, require this process. And I'll explain why. All the technologies that we have today were developed around 50 years ago, plus minus a decade. Even deep learning that is so trendy today, it's basically very large neural networks. A concept from the 50s matured around the 70s. And all of these technologies were developed for a specific type of problems. Problems such as text recognition, image processing, voice recognition. And for those problems, they work really well. They matured, and it's not considered innovation today that we can develop something that can understand what we say. It's almost a commodity. But all of those problems have one thing in common, and that is that they are very static. What do I mean by that? They don't change over time. The way English is being spoken hasn't changed for decades. We can take a model that was trained to understand speech, let it listen to JFK's recorded speech from decades ago. It will understand what's being said perfectly fine. Same thing about text. The way English letters are being written hasn't changed for centuries. We can scan text written centuries ago. They will be understood pretty easily. However, recently, people are trying to take the same technologies and apply them to human behavior. All of the interesting marketing use cases, predicting who is going to be the best customers, understanding trends in the market. Those are all human behavior prediction. And human behavior is very different than text recognition. Human behavior is very, very dynamic. It's being dominated by a very large number of very small, isolated, temporal signals. It's very, very dynamic, and therefore, it cannot be handled well with technologies that were developed for static problems. So what do people do? What do? We still have to predict who my best customers are going to be. So the only way to somehow generate predictions is to rely heavily on the semantics of the data and the semantics of the problem. This is why we often see data scientists becoming domain experts. We see someone who's a data scientist focused on fraud, data scientist that is an expert on loans. Either this, or they will have to sit side by side with a domain expert and work together. And this is why this process is so manual and iterative. Let's look again on the process that we've seen before. The first thing, as we all know, also probably most painful, cleaning the data. And cleaning the data, aside from being a very unpleasant task, is heavily related to the semantics. It's very, very difficult to do data cleaning if we don't really know what data are we dealing with. So data cleaning, a lot of domain expertise, and also machine learning expertise goes there. Then we have to do some feature engineering. And why? Because reality is raw data, but all of our machine learning technologies can work only with projection of reality to a feature space. Of course, the exception is deep learning. Touch that in a second. Feature engineering is, again, heavily dependent on the semantics. We need to know what we're looking for, the problem, and we need to know what we're working with, the data, in order to create high-quality features. Then comes the part of feature selection, selecting the model, and training, and all of this. There are many companies and very efficient tools that try to automate it, and they're really helpful. But when we go to this part, it means that we already spent all this time cleaning and feature engineering. Now, deep learning. It's true that deep learning can work directly with raw data. However, deep learning requires a lot of data, relatively speaking, and therefore, by definition, cannot detect recent changes in the data, emerging patterns. And therefore, it's really, really inadequate to predict human behavior that is actually dominated by those emerging patterns and recent changes. Once we have a working model, we know one thing for sure: it will immediately start to deteriorate. And why? Because human behavior is dynamic. There are temporal features that are basically the most important stuff, and we need to find them. They are gone because they are temporal, and we'll have to find new ones. So again, a lot of semantic works goes there. Okay, tough luck. How can we overcome this? Well, in order to overcome this limitation, a new paradigm of looking at data had to be developed, and this is what we've done. So we spent a few years at MIT working with a large variety of data sets, and we discovered something, I can say, fascinating. We discovered that there is a set of mathematical invariances that are guaranteed to happen in any structured human data. So I can look at any data. I don't need to know anything about the semantics of the data. I don't need to know anything about the demographics of the individuals who created this data, and I'm guaranteed that there is a certain set of equations that would take place in the data. Okay, fine. What is it good for? Well, if I have this set of mathematical invariances, which we call social physics, let me go one slide back, and if you're interested, you can read all about it in the book, Social Physics, that was recently published, because I don't have a lot of time now. So if I have these equations that I know must take place in any data, I can take data that I know nothing about, except that it's from human activity, and I can use social physics as a prior. I know that these things must take place in the data, so I can use it as a prior in order to extract groups of individuals that display dynamics in the data that infringe social physics invariances. How can this be? How can a dynamics in the data infringe something that I know must exist in the data? Only if those individuals have something in common in the real world. This is the only way that they can display such a too correlated behavior. What does it mean to infringe social physics invariances? It means to display something that cannot spontaneously emerge. So this is why we can take raw data sets and extract dozens of millions of what we call behavioral clusters. And at this point, no domain expertise is required, no machine learning expertise. Also, no data cleaning is required. Why? Because we take data and look for patterns that cannot spontaneously emerge, we are sort of robust to noise. And this is a very elegant trick, if I may say. Noise can never, is highly unlikely, to generate something that cannot spontaneously emerge. So noise can never mislead us. It can never create fake behavioral signals. If we add noise, it can disguise true signals. It can decrease the amount of information we can extract, but it can never create a false information for us. At this point, we took our raw data, whatever it may be, and we projected it to social physics representation, which is a large collection of behavioral clusters. Fully automatically, no expertise required. What do we do now? We ask questions. What is a question? Anything that I can give an example of. Here is a list of customers who recently purchased some product, find me more like those. What do? We match this list with our pre-extracted behavioral clusters. And whenever we find a cluster that has a lot of overlap with the list that I was given as an example, we know that this cluster has some relevance in the real world to the question that I'm supposed to solve. And notice that at this point, I know nothing about the semantics. I don't know what I'm being asked to find more of. I know nothing about what the data means, but I can still find lookalikes. I can still answer the predictive question that I'm being asked. And again, fully automatically. In addition, because we use social physics as a prior to the data, we can analyze data from very short periods of time. We don't need to analyze 5 years worth of data. In some cases, even 1 week is enough, which means that we can extract temporal features, exactly the interesting things that are indistinguishable from noise with all of the traditional techniques. They don't have enough statistical significance for any other technique to be distinguishable from noise, but if we use social physics as a prior, it gives us an additional information that can still allow us to detect them. This means that we get much more stable predictions. And finally, because everything is, the heavy lifting, the clusters is being done before we are being asked the questions, we can answer many questions simultaneously. It's very fast, it's extremely efficient. It's basically A to Z in minutes. We can take raw data, extract the clusters, and then ask a question. After a few minutes, get the answer. Everything is very easy. It's automatically scales up and down, deployed on the cloud, and very nice. So an example, this is one of our customers. It's a credit card company, and we connected to their data streams, and they had 25 different data streams. The obvious ones are everything that people purchased and every calls made to the call center, and a variety of other data streams. Some of them, we don't even know what they mean because the data arrived completely hashed. And because we are completely semantics agnostics, we can handle hashed data. So we connected to the data, and then they started sending us lists every day, a list of all the customers who took a loan in the last week. And what do they get from us? A list of all of their customers most likely to need a loan now. What do they do with this list? They call those customers and offer them a loan. And the result is tripling the amount of loans they actually sell. 3 times more loans actually sell in production with our prediction. Following this quite impressive success, they started asking other questions because you can ask whatever you want. So now they give us a list of all the customers who call the call center. They get from us all the customers most likely to call. What do they do with that? They send them a preemptive text message and achieve a significant reduction in their operational costs. And they ask, who is most likely to fly abroad? Who is most likely to buy a car? Whatever they want, they can ask, opening the bottleneck, and everybody's happy. Another example, this is actually how it looks. This is a Kaggle challenge that we ran through our system. What we have here is around 300 million point of sale purchases. And again, this is raw data. No features, no aggregated data. This is the raw data, also partially hashed. And the integration is just taking the data, the large CSV file, putting it on an AWS S3 bucket that we created for this purpose, and telling the system which column we want to ask about. So here it's the user ID. Basically, we can ask about anything here, but the Kaggle challenge revolved around predicting which customers are going to become a recurring shoppers. So we click on user ID, and the system crunches the data, extracting the behavioral clusters, and now we can start asking a question. The question is very easy to ask. It's a very straightforward process. We need to define 2 things: the search population and the desired behavior. And we can use native SQL queries here, and we even created this nice prediction wizard, allowing customers that don't even know how to use SQL to still use our system. So very easy, literally 5 minutes to define what this Kaggle challenge was all about. We click a button, wait a little while, and we get the answer. The answer is a ranking of all of the customers in the data, ranked by their likelihood to be what we wanted to find here, which is actually to convert with a certain coupon. And the system tells us the probability of each person. We can download the report, we can connect it with an API to a marketing system or whatever. 2 hours, A to Z, 2 hours. And regarding the performance, well, this challenge, almost 1,000 teams participated, and they were given 3 months. And you can see that the team who won the first place after us, they submitted almost 200 models. So they actually worked pretty hard. And as you can see here, our accuracy is significantly better than all of them. This actually even gained me, you remember? It was a bet. I told my co-founder that we would win, and I got a steak at Wolfgang and a bottle of wine. So, coming back to Jeff Dean's challenge. Can we replace domain expertise and machine learning expertise with computation? Our answer, yes, we can, and it's not even so computationally intense, but it would require us to take a very, very different approach about data. And to use, in this case, to use social physics, which is, as I'm sure that you now see, a very different way of doing predictive analytics. I hope I was able to give you a glimpse to social physics and how we can do data science automatically, and I would be very happy to answer questions. Thank you.
I'll start with one question, very, very basic question on the very principle of social physics. So why human activity? I mean, why is there a pattern in human activity that you don't find in other types of activity?
This is a very interesting question that I don't necessarily have the answer to, but we discovered that those patterns exist in human behavior. And sometimes they also exist in other types of data set, but we haven't been able to either prove or disprove it, so we focus on human data. But actually, sometimes we call it deep learning for human data, because it allows us to focus, not do generic machine learning, focus on one domain. And because we focus on one domain that we have a prior for, we can transcend the limitation of traditional machine learning.
Now, are there thousands of underlying rules and connections and structure that you found? Is that millions or?
No, a few.
A few. Okay, and I thought we were special as a species, but I guess not. We had a question up there.
Oh, sorry. So the examples that you gave, they were all very focused on, like, consumers. Is this also something that you could apply more to the business space, like, i.e. human behavior on the trading floor, for example?
Like predicting the stocks market?
Well, predicting behavior of the market in aggregate.
Naturally, a question that we are frequently being asked. And the issue there would be that we need the data to be on a user-specific level. Theoretically, if you did possess global trading data with exactly who did what, it might be able to be done, but I don't think that we have this data.
Very fascinating right here. Can you use that for recruiting?
For recruiting?
Yes, like for example, you have the top person and you look at this individual that you recruited and you want to find the next best person. So do you use those patterns to find somebody else?
HR, you mean?
Yeah.
So we actually been asked to do it to predict churn, so who is going to leave, to predict who is going to become a manager. Again, we would need the data for this. For example, all of the email correspondences. I'm pretty sure that if we were given access to these data sets, this would be pretty easy, but there is always the issue of privacy. So HR would not want to disclose all the emails, and this usually ends the conversation.
Which leads me, actually, that question leads me to my question. Where does the data come from, and how do you choose the dependent variable?
first question that we always run on customers' data, and they can customers can upload whatever data they wish. In this credit card company, as I said, we connected to 25 different streams, most of which we don't even know what they are. And we don't select the dependent variable. There are no, I mean, what do you do? What do you want to predict? Again, as I presented here, the only thing that has to do with the semantics is when the customer gives us the example of what they want to find more of, so the desired behavior. They give us an example, and at this point, again, we don't know what it means. We just find lookalikes. And before this point, there isn't anything that is even related to the question. The extractions of the clusters is done before we know what we want to predict. And once we are given the list of examples, we just find the clusters that have a lot of overlap, and the other members in those clusters are the answers, with some Bayesian statistics and information theory to sort of prepare one list.
So, sir. Just we'll have plenty of time to chat.
Hi. So I thought this was brilliant, but my concern is actually on adoption. So you've taken away the need for many people to collaborate on coming up with some idea or coming up with the answer to whatever input you've been given. And I work in a very large legacy corporation where, speaking of groupthink in social physics, there's a lot of, I really want to point the finger at the other guy if something doesn't work out. So I'm just curious, I mean, have you run into anything or any questions that have come up that say, well, you know, not everybody wants to be that decision maker, not everybody wants to be the one person who makes the decision, because suddenly if anything goes wrong, it's their fault.
But what's the alternative?
Well, they've been doing it for years. Look at financial services. It's a great success there. And I agree that it makes a lot of sense, and I would grab this in a heartbeat if I had it available. But I'm also concerned that even though there's value, it's not always used just because there's value.
Sometimes we actually get the opposite reaction when data scientists are afraid that it would replace them. But I actually don't think this is the case, because I think that nothing and no one can replace internal teams of data scientists and of analytics people, because they are the only ones who are familiar with data and their business, and therefore they are the only one who can come up with semantics features. And we see it when we work with companies that do have internal teams. When there are problems that they don't have time for, they use us. But for other problems that they do have homegrown models and a lot of semantic features, we can combine our insights with theirs and achieve a very significant uplift. So social physics is coming from a very orthogonal direction, detecting temporal features, a lot of very small isolated correlations, and it's completely agnostic to the semantics. Therefore, it cannot find the semantic features and that only internal teams can. And the answer to your question, we receive only positive labels, and I think this is what you meant. And we can also work with very, very small lists. So even 20, 30 positive samples, a sample of 20, 30 positive labels should be enough.
Great. Thank you very much. That's all the time we have for this, but you'll be around after this.
Thank you.